You want one language model that can be helpful, harmless, and funny, and you want to dial the mix at inference time with a preference vector. The standard approach conditions the model on that vector and trains it with online DPO, but here is the failure. Under different preference vectors, the model's reward distributions overlap heavily. The model does not really listen to the dial. MI-EPO's fix is information theoretic. It maximizes the mutual information between the response and the preference vector, so responses become genuinely distinguishable across preferences. One model, a clean preference dial, enforced by an objective, not by hope. Here is the mechanism. The key insight is that DPO is itself a mutual information estimator. When the critic is the implicit reward, the info NCE bound reduces exactly to the DPO loss, so the authors treat alignment as variational mutual information. They write one joint objective, the mutual information between the response, the preference feedback, and the preference vector. Then the chain rule splits it cleanly into two terms. One term aligns the response with each objective's feedback, that is, just per objective DPO. The second term maximizes mutual information between the response and the preference vector itself, which is the new piece. It pushes responses apart across preferences, killing the overlap. Where does this sit among prior work? Rewarded soups trains separate models and merges their parameters at inference, but a linear combination of weights cannot capture nonlinear trade-offs. Rewards. In context conditions, the policy on its reward vector with supervised fine-tuning, which is brittle. MOODPO is the strongest baseline, one policy, preference-conditioned prompts, online DPO. MI-EPO is a direct relative of MOODPO. It borrows the contrastive info NCE objective from representation learning and repurposes it for policy control. The whole lineage shapes the training signal. MI-EPO shapes it information, theoretically. The clean theoretical hinge. MI-EPO adds exactly one term to MOODPO, the exploration term. Set its weight beta W to 0, and the whole loss collapses back to scalarized MOODPO, term for term. That reduction is the falsifiable claim. Everything MI-EPO buys you lives in that one term. To keep training stable, the authors apply a stop gradient on the anchor logit, so the gradient flows only through the counterfactual preference vector, and the model cannot game its own self-generated samples. Minimal addition, and the baseline falls out as a special case. Now the numbers, safety alignment on Alpaca 7b with two objectives. The headline metric is hypervolume, which rewards both convergence and diversity across the preference simplex. MOODPO scores 1.54, MI-EPO scores 2.70. That is a 75% gain, computed straight from the table cells, and MI-EPO also wins on alignment and on conditional dispersion, meaning its responses are more faithful to the dial and more stable under A. Fixed preference. Best on every numeric metric, same backbone, same data, it holds on a second backbone. On Qwen 8b for a helpful assistant with two objectives, hypervolume rises from 1.68 to 1.98, and again, MI-EPO is best on all three metrics. The authors report a larger jump when they scale to three objectives, helpful, harmless, and humor, but those specific cells did not survive extraction from the paper, so I will only quote the qualitative claim, the advantage grows with the number of objectives, and leave the exact percentage unverified, and you can see the central diagnosis fixed. Under MOODPO, the reward distributions for different preference vectors sit on top of each other, a smeared cloud. Under MI-EPO, those distributions separate into distinct, lower variance clusters. That is exactly what maximizing mutual information between response and preference should do. The model is no longer ignoring the dial. Responses are informative about which preference produced them. The overlap shrinks, and the conditional control tightens. Oniscope. 5 caveats. First, no seeds, no confidence intervals, no significance tests on any table, all single-point estimates, and the second backbone gaps are small enough to sit within run-to-run noise. Second, only two backbones, Alpaca 7b and Qwen 8b, and two datasets, with at most 3 objectives, so the scaling claim extrapolates from very few points. Third, alignment is measured against open-source reward models, not human judgment, so the gains reflect reward model alignment. Fourth, the per-objective decomposition leans on an independence assumption that real preferences violate. Fifth, the alignment term outweighs the exploration term 10 to 1 in logit space, so in practice the objective is alignment-dominated. MI-EPO is the channel's first multi-objective alignment paper, and it reframes preference trade-offs as a mutual information problem. The chain rule decomposition unifies alignment and exploration under one information, theoretic objective, and the MOODPO reduction is the hinge that makes it falsifiable. One model, many preferences, a dial that actually works. Subscribe for the next paper breakdown.